Okay, so in the last one, we introduced the idea of rational functions and using partial fraction decomposition to integrate. I just threw these rules at you. Everything's super heavy in notation. So let's do an example to help us understand how to do this. So let me add one thing to these rules, since I just copy and pasted them from the last one, but we need to understand what everything means. This is when we're trying to integrate a rational function, right? We're calling q the denominator. And what we're going to try to do is rewrite this integral as an integral that's a sum of simpler fractions, okay? And so depending on the factors, that helps us determine what the factors of q helps us determine what these new simpler fractions are going to be. And we have these two rules. One is if we have a linear factor, it might be repeated, so a linear factor to some power, and you'll have fractions that are each successive power of that linear factor as denominators, and the same idea for irreducible quadratics. So this is the example I gave at the beginning of the last video to motivate this, but I showed you how to do it, how to get the answer, but I didn't show you how I got the decomposition that I used. So let's go through that process. So we're given this antiderivative. We're not sure which of our techniques will work. And so we're going to try this partial fraction decomposition, which means I want to rewrite this as the sum of some simpler fractions, okay? Now, determining what those simpler fractions are depends on the factors of q. So our first job is to look at q and see if we can factor it, right? And this one can certainly be factored into x plus 1, x minus 1, okay? So there's our first step. Now, I'm going to take this form of it and rewrite it as the sum of some simpler fractions, and I'm going to use the rule above and the rules above. And the rules above have to do with linear and quadratic factors. I only have linear factors, so the only rule I have to look at is if q has linear factors, I include a fraction with each with that linear factor, starting with a single copy of it, and then a squared, and then a cubed, up to whatever it goes to. Well, both of these are only linear factors anyways, right? In other words, this n is 1 for each of these. So what that means is I need to include a fraction with an x plus 1, and I need to include a fraction with an x minus 7, right? So each of these, oops, that's not 7, that should be a 1, pardon me. That's not how you factor that. All right, sorry about that. That's a 1, that's a 1. And then each of them should have a constant on top. I'm just going to call them A and B, right? So I'm using this rule for each of the factors, right? The rule is if Q has a factor of this, and we have one of each, so I'm going to use the rule for each of them. All right, now, how do I find A and B? Well, my first step is going to be to multiply each side of this equation by the denominator on the left. Okay. Now, what happens on the left is that these cancel, and I end up with x minus 7. And on the right, when I distribute this, so remember I have to distribute this, when I multiply this x plus 1, x minus 1 times the first term, the x plus 1 will cancel, and I'm left with a x minus 1. And when I multiply it to the second term, the x minus 1 cancels, and I'm left with b times x plus 1. Okay. All right, so there are a few ways to proceed from here. I'm going to go with my way, which I like better, though an argument can be made that there is a simpler way to do this. This is a more universal way. There's a simpler way, and if you find it out there, I'm happy for you to use it. but know that it won't always work. There are cases where it won't work, and this one will. So what I'm going to do now is I am going to distribute A and B. So I've got AX minus A plus BX plus B, and collect like terms, right? I've got an AX and a BX. In other words, I have A plus BX, and then I have a B minus A. Now, look at this equation. I've got two lines, right? X minus 1 is a line on one side, A plus BX plus B minus A is a line on the other side. If I'm claiming they're equal, it means that they're equal for all values of X. And for two lines to be equal, their coefficients, the slope and the intercept, have to be equal. In other words, A plus B has to be equal to the coefficient of X, which of course we don't write, but it's A1. And B minus A has to be equal to the constant -7. So writing that out, I get A plus B equals 1. And the constant is the same on each side. B minus A equals -7. So I've got a system of equations. I'm going to rewrite the second equation and put it under this one. I'm going to use the elimination method and add these two together. A plus -A is 0. I get 2B equals -6, or B equals -3. And if I take -3 and put it into this equation, -A equals -4, or A equals 4, which lets me know that I can now write X minus 7 over X squared minus 1. So I'm looking back at this here. A is now 4, so I've got 4 over X plus 1 plus -3 over X minus 1, right? And it's always good to check our work. So let's just do a quick check of this, right? If I wanted to add these two fractions together, I need to find a common denominator. In this case, it's the product of their two denominators. What do I get? I get 4x minus 4 plus -3 times x plus 1 is -3x minus 3 all over x plus 1, x minus 1. 4x minus 3x is x, minus 4 minus 3 is -7, and if you multiply the denominator, you get that. And so indeed, we have found a different expression for our integrand, and now integrating is a much simpler job. So remember, that was the whole point of this, that we can integrate this, and we can do that by rewriting it now using these two simpler fractions. And then, of course, I can use my rules of integration to write this as two separate integrals, and each of these is rather straightforward using natural logs. And there we have it. Okay. Okay, so that was about as easy of an example as we could do. So I'm going to do several more videos with more examples, and we'll keep adding layers of complexity. They are all going to have to do with these two rules up here, rewriting our fraction using the rules described up there so that we get something that's much easier to integrate. Okay, thanks everybody. I will see you in the next one.